Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 44. It's on simple harmonic motion. Imagine we take an object that's in equilibrium and we push on it. But it doesn't just move away. There's a restoring force that returns it towards equilibrium and another returning force that returns it towards equilibrium. And so what we get is this simple harmonic motion. What would be an example of this? Pushing a child on a swing. And so there are really two examples we'll do in AP Physics. One is a mass spring oscillator, and so it's going to bounce up and down like this, or a pendulum that's going to swing back and forth like this. So equilibrium is going to be right in the middle, but these restoring forces continue to bring it back towards equilibrium. And so if you have an object moving towards equilibrium based on restoring forces, we call that simple harmonic motion. And so here are the two types we'll talk about in AP Physics. Now, an important characteristic with each of these is the period of that harmonic motion. Period is always going to be measured in seconds, and it's time. So it's the time it takes on this oscillating spring to move from here to bounce up and then to bounce back again. Or for a pendulum to swing from here over to here and then back again. And so in a mass spring oscillator, how do we increase the period? Well, the easiest way to do that is simply increase the mass. As we increase the mass hanging from the spring, the period is going to get longer. How do we decrease it? Well, we can change the stiffness of the spring. As we make it stiffer, then we're going to make that period go down. What about a pendulum? How do we increase the period of a pendulum? Well, we do that by just simply changing the length of the pendulum. Now, what's interesting about pendulums is the mass doesn't have anything to do with it. And so how do we then decrease the period of the pendulum? Well, we have to change the gravitational field strength. As we increase that field strength, then we're going to decrease the period. And so with both of these forms of simple harmonic motion, you should be able to identify the position of the object at any time, its relative velocity and acceleration, and figure out when these are at a maximum and when they're at a minimum. And so let's look at some simple harmonic motion. This one we've got it horizontal with two springs, and so we can see its motion. Equilibrium is going to be right in the middle. And so as I pull it towards this side, there's going to be tension in this spring right here, and it's going to pull it towards the right. And so that restoring force is going to move it towards equilibrium. Now it's going to move in that direction. Now this other spring is going to move it back towards equilibrium like that. And so what we're going to get is this simple harmonic motion. What's cool about this one is there's an accelerometer with little LEDs so you can see the acceleration of the object. You can see right in the middle there's no acceleration right in the middle. And so what do you have to do in videos like this or in problems like this? You have to be able to identify the position of the object and the velocity and acceleration. When are they at a maximum? When are they going to be at a minimum? And so let's use this scenario. And so I'm going to pull that object towards the left. And so now I've let it go. And so at this point right here, as it's starting to move, where's our position going to be? It's going to be maximum towards the left. What about our velocity at this point? It's going to be minimum. It's going to be 0. And what's going to be our acceleration? Our acceleration is going to be maximum towards the right. We're going to have great acceleration at this point. Let's let it go for a second, and I've paused it again here right in the middle. What's our position? Again, it's minimum. It's at 0. What's our velocity? Well, it's accelerated, and now our velocity is at a maximum at this point. What's our acceleration? There's no acceleration right when it's in the middle. Let's let it go again. It's going to move over to this side. Now our position is maximum to the right. What about velocity? It's back to 0 again. Where's our acceleration? It's going to be maximum now towards the left. And so let's do some little experimentation with a mass spring oscillator. We're using a PHET simulation, and let's look at how the mass and that stiffness of the spring affect the period. And so I'm going to take a weight, put it on here, and then we'll measure the period just qualitatively. So that's going to be the period. So that's a 50-gram mass. Now let's put a 100-gram mass on there, and let's listen to the period again. Okay, so you can see that we're slowing down the period as we increase the mass. Let's put 250 grams on there. So you can see that as we increase the mass on that spring, then we're increasing the period. But now let's play around with the stiffness of the spring. We call that the spring constant. So now I've made it a stiffer spring. I put that 250-gram mass on it, and you can see the period is now decreasing. And so by increasing the stiffness of the spring, we are decreasing the period rather of the spring. Now let's really make it a soft spring. What happens? You can see the period gets really, really large. And so in summary, what have we learned just from this experimentation? That if you increase mass, you're going to make a longer period for that harmonic motion. And if we increase the stiffness, then we're going to make it a shorter period. If we look at that quantitatively, so if we look at the actual period of a spring like this, what's really affecting it are two things, the mass and the spring constant. And so you can imagine just looking at this algebraically, if we increase mass, what's going to happen to the period? The period is going to increase because it's in the numerator. What's going to happen if we increase the constant of the spring, or the spring constant, as we make it stiffer, as this number gets larger in the denominator, then we see that the period is going to become less. Now let's look at a pendulum. Again, another PHET simulation. So I'm going to move this to the side. I'm going to try to drop it at about a 30-degree angle. And this one has a little photo gate timer so I can time how long it takes back, or how long it takes to get back to that original position. So we can see here that we've got a period of 2.862. Now I'm going to make the pendulum have a smaller length, dropping it from the same angle, and you can see that the period now is less. It's 2.415. Now let me make it even less. I'm going to try to drop that weight again at a 30-degree angle. Set my photo gate timer, and you can see that the period is becoming less. So as we decrease the length, what are we doing to it? We're speeding it up, or the period is decreasing. Now watch what happens as I change the mass now. As I change the mass, drop it from a 30-degree angle, start my photo gate timer, you can see that it doesn't affect it. So mass doesn't affect the period. But what does, remember, is going to be the gravitational field strengths. So now let me change it to the moon, and you can see that the period is increasing, it's slowing down. Let me change it to Earth. Now it's speeding up. What happens if we make it Jupiter? It's really speeding up. Or if we make it nothing, it just continues moving like that. So if we look at that quantitatively, or rather qualitatively, as we increase the length, we got a longer period. And as we increase the gravitational field strength, then we got a shorter period. If we look at that algebraically, this is the equation. Length is going to be on the top, you remember. And so as we increase the length, we're going to increase the period of the pendulum. What happens as we increase gravitational field strength? As we increase that, then we're going to decrease the overall period of the pendulum. Okay, did you learn to predict which properties affect harmonic motion? Again, it's a restoring force moving it back towards equilibrium. Could you design and plan and collect data to ascertain what characteristics are affecting the period? Again, in a spring, it's going to be the mass and the stiffness of the spring. If we're looking at a pendulum, it's going to be the length and the gravitational field strength. And finally, could you figure that out quantitatively? What happens as we increase length, for example, to our period, or gravitational field strength? Well, I hope so, and I hope that was helpful.
Understanding the concept of periodic motion. The motion of an object that repeat its path regularly after equal interval of time is called periodic motion. For example, motion of the mass attached to elastic spring. We know that this mass repeats its back and forth motion over the same path after equal interval of time. So it is in the periodic motion. Secondly, motion of the earth around the sun. We know that the earth moves over the same circular path and repeats its motion after equal interval of time. So it is also in the periodic motion. Thirdly, motion of the hands of a clock. And fourthly, motion of the pendulum. These are the different examples of periodic motion because they move and repeat their respective motion over the same path after equal interval of time. Now let me teach you that periodic motion is further divided into two types of motion: oscillatory motion and non-oscillatory motion. Here, what is oscillatory motion and what is non-oscillatory motion? Well, periodic motion in which object moves back and forth or up and down from a fixed point is called oscillatory motion. Or simply you can say that up and down or back and forth periodic motion is also called oscillatory motion. For example, the motion of a mass attached to elastic spring. the motion of a simple pendulum, strings of the guitar. These all objects move back and forth from a fixed point, so they all are in oscillatory motion. While periodic motion, in which an object doesn't move back and forth from a fixed point, is called non-oscillatory motion. For example, motion of the earth around the sun. The earth doesn't move back and forth, but it repeats its motion on a circular path. So it is a non-oscillatory motion. Secondly, the motion of the fan and the motion of hands of a clock. These all objects move and repeat their respective motion on a circular path. So they all are a non-oscillatory motion. From these examples, we learn that every oscillatory motion is periodic motion. For example, the motion of a mass attached to elastic spring is periodic as well as oscillatory motion. Also, the motion of a simple pendulum is periodic as well as oscillatory. Secondly, we learn that not every periodic motion is oscillatory motion. For example, the motion of the earth is periodic but not oscillatory. The motion of hands of a clock is periodic but not oscillatory. Thus remember that every oscillatory motion is periodic motion, but not every periodic motion is oscillatory motion. Now, oscillatory motion is divided into two types: SHM or simple harmonic motion and non-SHM or non-simple harmonic motion. Firstly, we will understand SHM, and finally, as a bonus tip, I will give you an example of non-SHM. So, understanding oscillations and SHM. Let's consider a mass M attached to elastic spring. Now, I displace this mass M from its mean position. Let the displacement of the mass from its mean position is x. Due to displacement x, restoring force F produces in the elastic spring. Let me repeat it. Due to displacement x, restoring force F produces in the elastic spring. This restoring force produces acceleration in the mass. As a result, mass moves back and forth at its mean position. Now listen carefully. If the size of displacement x of the mass is small, the size of restoring force F will also be small on the mass M. If I increase the size of the displacement x, the size of the restoring force F will also be increased. Thus, we therefore write F is directly proportional to x. Secondly, the direction of displacement and the direction of the restoring force are opposite. So I write F is directly proportional to negative x. Now to eliminate the sign of proportionality, we have to put some sort of constant. Thus we get F is equal to negative k into x. K is the spring constant. I call this equation number 1. We have learned that restoring force F also produces acceleration A and the mass M. So according to Newton's second law, we get F is equal to ma, and I call it equation number 2. Now comparing equation number 1 and equation number 2, I get ma is equal to negative k into x. Rearranging the equation, I get a is equal to negative k over m into x. We know that k is the spring constant and m is the mass attached to the elastic spring. These both quantities are constant. So acceleration a of the mass m purely depends upon its displacement x. And also remember that the direction of acceleration will be opposite to the direction of displacement. Hence, we define SHM or simple harmonic motion as when force on oscillating object is directly proportional to the displacement from its mean position is called SHM. Let me repeat it. When force on oscillating object is directly proportional to the displacement from its mean position is called SHM. Also remember that in SHM, acceleration is also directly proportional to displacement. Therefore, in oscillatory motion, F force is directly proportional to displacement and acceleration is also directly proportional to displacement. We also call this oscillatory motion as SHM or simple harmonic motion. Remember these two properties of the simple harmonic motion. Finally, as a bonus tip, let me teach you that not every oscillation is SHM. For example, when you drop a ball from a certain height h on a perfectly elastic and plane surface, the motion of the ball is oscillatory but not SHM. It is because the restoring force on the ball is provided by its weight W is equal to mg, not by the vertical height h. This was all about periodic motion, oscillatory motion and SHM.
In June 2001, officials in London unveiled a striking new feat of engineering, the Millennium Bridge, a pedestrian bridge spanning the River Thames. It promised to be very useful and it was cool to look at, but it had to be closed almost immediately, because when people used the bridge, it swayed back and forth noticeably due to the force of their footsteps. Undeterred, people kept using the bridge, but as they walked, they began to lean into the swaying to keep themselves from falling over, and that only made things worse. Eventually, the motion of the bridge became so severe that the bridge took on the shape of a giant S, essentially a horizontal wave. The bridge had to be closed and the engineers took nearly 2 years to fix the problem. So what was wrong with the Millennium Bridge? And why didn't the engineers foresee the problem? The answer lies in oscillations. The physics that caused the swaying of the Millennium Bridge has to do with oscillations, or back and forth motion. Or more specifically, it has to do with simple harmonic motion, where oscillations follow a particular consistent pattern. But before we had the Millennium Bridge as a real-life example, physicists often described simple harmonic motion in terms of a ball attached to a horizontal spring lying on a table. While it's lying there at rest, it's in equilibrium. And when you move the ball so that it stretches the spring, then let go, the ball keeps moving back and forth forever. In a frictionless world. That back and forth motion caused by the force of the spring is simple harmonic motion. Now, we want to know two things about this oscillating ball. What kinds of energy does it have? And what's its maximum velocity? To better understand what's happening to the ball, let's start with its energy. As the ball compresses and stretches the spring, both kinetic energy and potential energy come into play. Kinetic energy is the energy of motion, and as the ball moves, there are 2 points, the turning points, where it's not moving. One point is where the spring is compressed all the way, and the other is where it's stretched all the way. And the distance between either of these 2 points and the equilibrium point is called the amplitude. At those 2 turning points, the ball won't have any kinetic energy since it isn't moving. Instead, all of the ball's energy will be potential energy from the spring, half of the spring constant times the amplitude squared. Now, as the ball moves towards the middle, its kinetic energy starts to increase because it's moving faster and faster. And at the same time, its potential energy decreases, keeping its total energy the same. And exactly in the middle of the ball's motion at the equilibrium point, its potential energy goes down to 0. The ball is back where it started, so the spring is no longer pulling on it. Its kinetic energy, on the other hand, has reached its maximum, which means that at that point, the total energy of the ball will be equal to half of its mass times its maximum velocity squared. Now we have 2 equations for the total energy in this oscillating spring, which we can combine into one equation. And if we use algebra to move around its variables, we can start to answer the second question we had about the ball. We wanted to know the ball's maximum velocity, and this equation tells us that it's equal to the amplitude times the square root of the spring constant divided by its mass. So we've answered our two questions about the ball on the spring. We know about its energy and we have an equation for its maximum velocity. But there's a lot more going on with this ball than just its energy and velocity. It also has properties like period, a frequency and an angular velocity, plus its position changes with time. You might recognise those terms because we already talked about them in our episode on uniform circular motion, and that's no coincidence. Simple harmonic motion is actually a lot like uniform circular motion, mathematically speaking. You can see this for yourself if you compare the ball's motion on the spring to an object in uniform circular motion, say a marble moving along a ring at a constant speed. Okay, I admit it might seem like kind of a weird comparison at first. For one thing, the ball on the spring is moving in one dimension, while a marble moving along a circular path is in 2 dimensions. But what if you take that ring and look at it from the side? The marble keeps moving along its circular path, but to you, it looks like it's just moving back and forth along a straight line. Not only that, but it looks like this marble is stopping momentarily as it changes direction and moving faster as it gets closer to the middle, which is exactly the same way the ball was moving on the spring. Now let's take this comparison one step further. Let's assume that the radius of the ring is the same as the amplitude of the ball's motion on the spring, and that the marble's constant speed along the ring is equal to the maximum speed of the ball on the spring. In that case, if you did the math, you'd find that the equation for the marble's velocity when you look at it edge on is exactly the same as the equation that described the velocity of the ball on the spring. So let's recall what we know about uniform circular motion to see what it can tell us about simple harmonic motion. We know that the time it takes for the marble to move around the ring once is called the period. We also know that the period will be equal to the circumference of the ring divided by the marble's speed. And the radius of the circle is the same as the ball's amplitude on the spring. So its circumference will be equal to 2 times pi times the amplitude. This means that the period will be equal to 2 times pi times the amplitude divided by the marble's speed, which again is the same as the ball's maximum speed as it moves on the spring. And we can simplify that equation since we know that the maximum speed of the ball is equal to the amplitude times the square root of the spring constant divided by the mass. So the period of the marble's motion around the ring is equal to 2 pi times the square root of m over k. Now we've also talked about the frequency of uniform circular motion. It's the number of revolutions the marble makes around the ring every second, and it's equal to 1 divided by the period. In this case, the frequency will also be equal to 1 over 2 pi times the square root of k over m. And that'll apply to the ball on the spring too, because the rules are the same. Finally, there's angular velocity to consider. In uniform circular motion, we've described it as the number of radians per second that the marble covers as it moves around the ring. And angular velocity is just equal to the frequency times 2 pi, which means that in the case of the ball on the spring, it's equal to the square root of k over m. So now, with the help of our knowledge about circular motion, we can understand the period, frequency and angular velocity of the ball's simple harmonic motion as it oscillates on the spring. But there's one more question. How does the ball's position change over time? To find out, we'll have to analyse the marble's motion along the ring again, and the answer will involve some trigonometry. But it's not particularly complicated trig, so it'll be fine. At any given point along its path, the marble will be at a certain angle to the right-hand side of the ring, and the cosine of that angle will be equal to its horizontal distance from the centre of the ring divided by the ring's radius. We already know that the radius of the ring is the same as the amplitude of the ball's motion along the spring. And if you turn the ring so it looks like a line again, you can see that the marble's horizontal distance from the centre of the ring is the same as the ball's distance from the equilibrium point. So the cosine of theta is equal to the ball's position divided by its amplitude. In other words, the ball's position is equal to the amplitude times the cosine of the angle. And we can simplify this equation too. In the same way that distance is equal to velocity multiplied by time, the angle is equal to the angular velocity multiplied by time. So we can write the equation for the position of the ball as x equals a cosine omega t. And when you graph this equation, something interesting happens. It looks like a wave. We'll be talking a lot more about waves in our next 3 episodes, but for now, it's helpful just to see the connection here. For an object in simple harmonic motion, the graph of its position versus time is a wave, which is why the swaying of the Millennium Bridge looked like a wave. Speaking of the bridge, we can now better understand what happened to it. The bridge's shimmy was the result of oscillation, but it was made worse by another culprit. Resonance. Resonance can increase the amplitude of an oscillation by applying force at just the right frequency. Kind of like how you can get a kid on a swing set to swing higher by pushing at just the right moment. The engineers of the Millennium Bridge were reminded of that the hard way. When pedestrians on the bridge started to lean into its swaying, they created resonance. They amplified the amplitude of the oscillation. And the engineers of the bridge did account for oscillations caused by resonance when they designed it. But they only considered the vertical oscillations, the kind that would have made the bridge bounce up and down. They didn't realise that they'd also had to factor in the horizontal swaying caused by people walking. So it was only a tiny bit of swaying at first, but it got a lot worse because people were leaning into their steps, causing resonance. In the end, engineers had to apply a series of changes to the bridge to counteract its oscillations. Because if there's one thing you don't want your bridge to be doing, it's the wave. Today you learned about simple harmonic motion, the energy of that motion, and how we can use math of uniform circular motion to find the period, frequency, and angular velocity of a mass on a spring. We also described how the position of an object in simple harmonic motion changes over time.